So here is what this chapter is about. Oops. Okay, so this chapter is about currents, electric currents, and we'll talk about resistances as well, things that resist electric currents. Okay, so what what we did was the last 4 chapters we talked about charges, they were at rest, and now we are getting the charges to move, and that's so we're going to talk about electric currents in the next few chapters. So this chapter will introduce electric currents. Then we'll look at electric currents in various circuits. We'll start off by looking at direct current circuits, that is currents that do not change direction. And later on, in one of the later chapters, we'll talk about AC currents. Okay. Then we'll introduce magnetic fields. And then what we'll study in the next, in chapter 12, is that moving charges, electric currents, produce magnetic fields. Okay, so that's what we'll look at. So that's the structure for the next 4 chapters. Those are the topics that we're studying. Okay, so we'll study the motion of charge, which we'll call electric currents, and the effect of these electric currents. Okay, besides the fact that they make electric motors work, this, that, and the other. Okay, they also produce moving charges produce magnetic fields as well. Okay, so that's what we'll study. We've said this several times. Maxwell's equations summarize all electromagnetic phenomena. So these 4 equations here, I'm just showing you these equations because eventually you'll see them, and we're not studying them now, but you'll study these equations in junior and senior level classes if you're an electrical engineer anyway. Okay, so these 4 Maxwell's equation summarize all electromagnetic phenomena. This 5th equation tells you the force on a charge in the presence of an electric field and the force on a charge in the presence of a magnetic field. We'll look at this portion of the equation in chapter 11. Okay. Chapter 12, we'll look at this portion of the equation. What this equation tells you is this is electric current density, electric currents producing magnetic fields. B denotes magnetic fields. Okay, so this is electric current density producing magnetic fields. Okay. Anyway, so that's what these. So these are the 4 Maxwell's equations in differential equation form, the same equations in integral forms. All right, so in this chapter, what we are studying is currents, electric currents. Here's what happens. So let's go to the chalkboard. So here's a piece of metal. Here's a conductor. Okay. Now what we'll do is, so the conductor has these atoms. In a conductor, the atoms which are neutral will lose a couple of their outermost electrons. And what you have is the free electrons moving around in this conductor. Okay. Now, what we'll do is, if you connect a battery to this conductor, what the battery does is it establishes the electric field in the wire. Okay. So everywhere in the wire, as soon as you connect the battery, it establishes an electric field at the speed of light inside the conductor. Okay. Now, these electrons, okay, so where is it gonna better label it, the electric field? Okay. Okay. So as soon as you turn on this electric field, the electrons respond to the electric field and they drift in that direction, okay? So now the electrons will drift in this direction, okay? And we'll talk about drift velocity in a second, more details about that. Okay, so these electrons move in the wire and they start off with from the negative, well, the whole chain of electrons moves. So electrons move from the negative terminal to the positive terminal like that, okay? Back in the old days, the electrons had yet to be discovered and we'd already been working with electricity, and the convention was current flowed from the positive terminal to the negative terminal, okay? Now we know that, so in conductors and metals, it's electrons that carry electric current. But we'll stick to the convention. The direction of the current is that, from the positive terminal to the negative terminal. So that's what's happening at a microscopic level. And we'll talk more about this in detail, okay? So that's what we are talking about here. We're going to be talking about electric currents. Okay. So here are some of the topics. Currents. We'll talk about current density. That's the J that you saw in a little bit ago. Drift speed. That's what I was mentioning. The average speed of the electrons due to the presence of electric field. Okay. And we'll talk about Ohm's law, which is the more practical law. Relating the currents to voltage and so on. Okay. All right, so let's try and understand this diagram. In this diagram, you can see that here's a battery and here's a bulb. This is a switch. When the switch is open, there is no closed circuit for a current to flow, and the bulb doesn't glow. You close the switch and the bulb glows because a current is flowing through the bulb, and that lights up the bulb. Now what this thing is showing you is, so this is the positive terminal of the battery, there's the negative terminal of the battery. Now this diagram shows you if you switch the terminals, the bulb glows equally bright. Okay, so what we're saying is the bulb doesn't care whether the current is flowing this way or that way. Okay, it glows equally bright. In this diagram, you connected two bulbs in series, and these guys do not glow as bright as that guy. Okay, so what you learn is the resistance has doubled and the current has halved. And since the current is lower, the power dissipated in each one of them is lower. The power dissipated is I square R. Since the current is halved, this is glowing 1/4 as bright as that bulb. Okay, but you'll see all of that later. In this diagram, you connected two batteries, the voltage doubled, and the bulb is glowing twice as bright as that guy. In this guy, these two bulbs are connected in parallel, and the current in each one of them is the same as that, and they're glowing as bright as that. Okay, so if you ask what is the difference between these two guys, in both cases, the bulbs are glowing as bright. In this case, twice as much current is being drawn as out of the. So the energy is being drained twice as fast. So that diagram was about. Okay. So now let me show you a little simulation of electrons in a metal. Okay. So what we are seeing is the following. So I showed you this diagram. These were the positive ions, and here are the electrons. And these free electrons, if there was no electric field, would move about randomly, and they're moving about and colliding with the positive ions. And they move about 1,000 kilometers a second. Okay, so they're moving about extremely fast. And that's what this thing models. All right, so that's what this thing is modeling. See, the electric field is 0, meaning we have not connected a battery to this metal. By the way, so in the previous chapters, we had said that electric fields in a conductor is 0. That's in the static situation. You can have if you connect a voltage source, that can establish an electric field in a conductor. Yeah. So when the electric field is 0, the electron, each time you see a sharp corner, that's when it's collided with the ion, the atomic ion. And so here's an electron moving about freely in a metal wire, okay? And you see it won't go anywhere. Now, if I turn on an electric field, meaning I've connected a battery, now the electron starts drifting in the opposite direction, okay? And the drift velocity on the average is very low, okay? So on this motion of 1,000 kilometers a second, there's a drift velocity of about 1 millimeter a second, okay? So that's the drift velocity. All right, so that's what we're saying here. So when electrons move through conductors, the path zigzag, and as they collide with atoms, the speed between collision is 1,000,000 meters per second, or 1,000 kilometers a second. So in the absence of net electric and external electric field, in the absence of no voltage source, no flow of electron will occur, okay? By the way, these are, so the time between collisions, so mean time between collisions denoted by tau, is 10 to the minus 14 seconds. So an electron collides with an atom, and then it'll collide with the next atom within 100 trillionth of a second. That's what that number is saying. And it travels about 10 to the minus 8 meters between collisions on the average. So if it collided with an atom here, it 10 to the minus 18, minus 8 meters is roughly about 100 atoms later, it'll collide again. Okay, so that's what that means. All right, so here is a conductor connected to a battery. So when a conductor is connected to a battery, it sets up an electric field inside the conductor. Okay, so with the voltage source, you can set up an electric field inside a conductor. And that's what this diagram shows you. So when a voltage source is connected to a conductor, it establishes an electric field inside a conductor. Okay, so it's established a electric field in the connecting wires and your resistor. Okay, and if you have free charges, they'll respond to this electric field. So if this was a piece of wood, for instance, none of these there wouldn't be any free electrons. And so even if you establish an electric field, there would be no current, okay? All right, so when you establish an electric field, so let's say you established, so this is inside a conductor, you've established this electric field, the electrons will drift slowly in the opposite direction, okay? So the motion of the electron is complicated. There's this random motion, and on top of this random motion is this overlaid drift speed, okay? And the drift speed for typical currents, so for a 10 amp current, the drift speed is about 2 times 10 to the minus 4 meters per second. That's about 0.2 millimeters a second, okay? So the drift speed is very small, okay? So here's a question for you guys to think about. So if drift speed is so slow, why does a light come on as soon as the switch is turned on? Okay. So what we're saying is, the following. So let's say here's a light bulb. Okay. And this is connected to a battery. And here's a switch, okay? And what we're saying is the instant you close the switch, when you close the switch, the battery seems to come on, and the light bulb seems to come on instantly. And I sort of gave you the answer to this. What happens is the minute you close the switch, the instant you close the switch, you're establishing an electric field throughout the loop. And as soon as an electric field is established, the electrons start drifting in the opposite direction. Okay, so electrons everywhere start drifting in the opposite direction. Now it turns out that this electric field is established at the speed of light, and soon as wherever the electric field is established, the electrons immediately respond. Okay, so that happens so fast it appears instantaneous to you guys. Okay, it's instantaneous to us. All right, so now let's finally define electric currents. So here's a wire. And the electric current is defined as you can stand at any location, and the amount of charge passing you per second is called the electric current. So the amount of charge passing you in that time, so that the ratio gives you the amount of charge passing per unit time. So I is dq by dt, again, the amount of charge passing you per second. The units for current are charge is measured in Coulomb, time in seconds, Coulomb per second. And this combination is called an ampere after Mr. Ampere, who studied electric currents and so on. Okay, so an ampere is the unit for electric currents. So here are some typical currents that we encounter. Okay, so here's a scanning tunneling microscope where the current is almost about a trillionth of an ampere. When your neurons fire, the current is a nanoampere, roughly. In a wristwatch, the current is about a microamp. Your cell phones use currents of milliamps or milliamps. The 100-watt light bulbs uses a current of 1 amp, okay, and so on. In a lightning bolt, the current is about 10,000 amps. The auroras, the currents there involved is 1,000,000 amp, and so on. And this is a heliospheric current sheet where the current is about 1 billion amps. Okay, and what this is made up of solar wind, and that solar wind gets compressed into a thin sheet because of the magnetic field of the sun, and that's called the heliospheric current sheet. Anyway, so these are some of the currents that you see. Okay, so the conventional direction, current direction is, it's convenient to assign a current in the same direction as the flow of positive charges. So again, like I said, this convention was adopted before we knew about electrons, but so here's the battery, this is the positive terminal of the battery, there's the negative terminal of the battery, and current was assumed to flow in this direction. Okay. Now in metals, we know that it is electrons that flow in that direction. Okay. So that's the opposite direction of the direction of current flow. Okay. So the convention was the currents flow in that direction. Okay. Now, if you have both positive and negative charges, so what this diagram is showing you is, in this diagram, the electric field is established in that direction from right to left. Electrons flow in that direction. If you had both positive and negative charges, in this case, the electric field is in that direction. positive charges are moving in that direction and negative charges in the opposite direction. In this case, the electric field is in that direction. All positive charges are moving in that direction. Okay. So this has a electric field in this direction again. Okay. So in conductors such as copper, motion of electrons give rise to currents. In conductors like in metals, the charge carriers are electrons. Okay. And so their motion gives rise to currents. In electrolytes and gases, so in plasmas and stuff like that, you have both positive and negative charges carrying currents. Current is a result of both flow of positive and negative charges. You can have certain kinds of semiconductors where things called holes, which holes are essentially missing electrons, and they're treated as positive charges. Their holes carry currents. Okay, so those are treated as positive charges. All right, so here is a microscopic model of currents. So here's a wire, and current is, so if electrons are flowing in that direction, current is flowing in this direction. But for now, let's say these are positive charges moving in this direction. Okay, so the average value of the current is the little n, which is the charge density, the carrier charge density, how many free electrons there are per meter cube, or whatever the charge that is carrying the current. Q, the charge of the carrier, VD is the drift velocity, and A is the area of cross-section of the wire. Okay. So that's how the current is related to the speed of the electrons, for instance, if electrons are the charge carrier. Okay. So that's the drift speed. And again, remember that's about 0.2 millimeters per second. Okay. So very slow. All right. So we will define a quantity that's useful. Current density. Current density is the current flowing through this wire. So there's a current, the purple arrow, that's the current in response to this electric field. So the current divided by the area of cross-section of the wire, okay? So the current density is current per unit area, and that's equal to the carrier charge density N times the charge of the carriers times the drift velocity. Now, the reason we define this current density is it turns out that the current density is proportional to the electric field. It's proportional to the electric field. Stronger the electric field, you double the electric field, the current density doubles. Okay. And this constant, the proportionality constant, is called the conductivity of the material. It's the property of the material. And sometimes it's also useful to define the resistivity. Oftentimes it's, okay, so conductivity and resistivity are inversely related. Higher the resistivity, lower the current density, and so on. Okay. Higher the conductivity, higher the current density. Okay. All right, now it turns out that it's hard to measure current density using instruments and the electric field and so on using macroscopic instruments. What is easy to measure is the voltage across a wire and the current flowing through a wire. So we'll write this relationship in terms of quantities that are easier to measure rather than electric field and current density. Okay, so back we saw that if there's a constant electric field in this wire, the voltage across this wire would be the electric field times the length. Now the electric field is related to the current density is J over sigma. Electric field is, so from this equation, the electric field is J over sigma. Sigma is the conductivity. Okay. And and then the current density is current divided by area. Okay, so let me go to the chalkboard. Okay, so So here's a wire. We've established an constant electric field in the wire. The length of the wire is that. So the voltage across the wire is E times L. J is sigma E. So E is J over sigma. Okay, J over sigma. Now I is J over area. Okay. Oops. J is I over area. Okay. So you have I over area sigma L. So this is L A sigma times I. Okay. L is the length. Okay. And this quantity is called the resistance of the wire. Okay. And so voltage is resistance of the wire times the current in the wire. Okay. And this is known as Ohm's law. Okay. And this is the useful form of Ohm's law. Okay. So this is easy to measure using a macroscopic instrument. This is easy to measure. And these are all quantities that are easily measured using macroscopic instruments. Okay. So, and that's Ohm's law. So the voltage across a conductor is equal to the resistance of the conductor times the current passing through the conductor. So if you double the current in the conductor, the voltage across it will double. Or if you want to double the current, you have to double the voltage. So the resistance of the wire depends on the length of the wire, the area of cross section, and the conductivity. Okay. So the resistance of the wire depends on the length of the wire, the conductivity, and the area of cross section. Also, the conductivity was related to the resistivity, like so. So it's oftentimes you see the resistance given in terms of resistivity, length, and area like that. Okay, and you will be doing a lab related to this formula. So you'll do a lab where the resistance is related to resistivity, length, and area like that. Okay. So this guy is called resistivity. This guy is the resistance of the wire. And of course, that's the length of the wire and area of cross section. Okay. All right, so here's Ohm's law. Ohm's law says that the voltage across a resistor is its resistance times the current flowing through it. So there is the resistance of a wire, and it depends on the resistivity, length of the wire, and area of cross section. Resistivity and conductivity are inversely related. And so you see, here's this quantity is a characteristic of the material, and it's important enough where you find tables listing them. So you can see for metals, the units of resistivity are ohm meter. And by the way, the units of resistance are ohm, in honor of Mr. Ohm, who studied, investigated these types of things. So resistance are measured in ohms. This quantity, resistivity, for metals is about 10 to the minus 8. And for carbon, it's 10 to the minus 5. So has a fairly, it's carbon is conductor, but its resistivity is about 1,000 times greater than copper. So carbon would, graphite would be 1,000 times less conducting than copper. You can see that rubber has a resistivity of 10 to the 13. Okay, so if you connect a battery to a rubber wire and a copper wire, the current in the copper wire would be 10 to the power of 21 times greater than in the rubber wire. Okay, so that's what those numbers mean. And here's a temperature coefficient. What we find is in most materials, as you increase the temperature, the resistance increases, and that's what this temperature coefficient is related to. All right, we'll pause now and give you guys a chance to ask